objectives of today's lecture will enable you to understand the nomenclature of disubstituted benzene, the physical properties, structure on the basis of molecular orbital theory, and we are going to discuss the concept of resonance. Students, let us start with the nomenclature of disubstituted benzene. When there are two substituents on benzene ring, their relative positions are indicated by prefixes like ortho, meta, and para in common system of naming. And we are going to represent their positions by numerals or numbers while we are going to name them according to IUPAC rules. Let us apply both of these rules on these two compounds. As you can see, the first compound, two methyl groups are present at 1 and 2 positions adjacent to each other. Such a position relative to each other is called ortho position. When the two substituents are present at 1 and 3 carbon with respect to each other, it is called as the meta position. And if the two substituents are at 1,4 position with reference to each other, it is called as the para position. Now let us apply these rules and name them according to common system. The first one is ortho-dimethylbenzene. This is the ortho position. The second one is meta-dimethylbenzene, and the third one is para-dimethylbenzene. Now students, if we are going to apply IUPAC rules, the names are going to be 1,2-dimethylbenzene for this compound, 1,3-dimethylbenzene for the second one. This is carbon number 1, 2 and 3. And third one is, this is carbon number 1, 2, 3 and 4. So the name is going to be 1,4-dimethylbenzene. Students, another rule is, if the substituents are different and one of them is an alkyl group, the numbering is started from the ring which is linked to that alkyl group, and the second substituent gets the lowest possible number. Now students, look at this compound. You can see that one of the substituent is an alkyl group, a methyl group, and the second is chloro group. So the lowest number will be assigned to the alkyl group, and the second gets the lowest possible number. Over here, we are going to start numbering from this carbon atom 1, 2, 3, 4, 5 and 6 instead of numbering it the other way around, which is not going to give the second substituent the lowest possible number. So the name is 2-chlorotoluene, or in common naming, it is going to be called as orthochlorotoluene. The third rule is, when a common name is used, the substituent which is responsible for the common name, for example, when CH3 is attached to the benzene ring, it is called toluene. So CH3 is responsible for the common name. And in phenol, OH is responsible for the name phenol. So the OH and CH3 are going to be considered as carbon number 1, and numbering is going to start from this carbon atom bearing that group. And such a compound is called as the derivative of that compound. Look at these examples. Students, you can see that if we are not having chlorine, then this group is called toluene. Now we are having a chlorine on the second carbon atom or on the ortho position. So CH3, this carbon to which CH3 is attached, will get the lowest number, which is 1, and second to the substituent. That is why it is called orthochlorotoluene or 2-chlorotoluene. 2-chloro obviously indicates that this methyl is getting carbon number 1, and 2-chlorotoluene is the derivative of toluene now. Similarly, look at the second example. If we are not having chlorine over here, this is the structure of phenol. We are having chlorine on the third carbon atom. So it is metachlorophenol or 3-chlorophenol. So 3-chlorophenol is the derivative of phenol. Another example is para-bromo-nitrobenzene. Now if we are not having bromine over here, this is nitrobenzene. And para-bromo-nitrobenzene is the derivative of nitrobenzene. The IUPAC name is 4-bromo-nitrobenzene. Now students, When two substituents are different, they are usually put in alphabetical order. Look at this example. One is nitro, the other one is bromo. B is going to precede N. That is why the name is para-bromo-nitro-benzene or 4-bromo-nitro-benzene. Now students, let us learn the rule for polysubstituted benzene. Polysubstituted benzenes are named by numbering the substituent to the ring as to give the substituent lowest possible numbers. The last named substituent is assumed to be at position number 1. This number is not indicated in the name. Look at the first example. It is 2,4-dichloroaniline. Now when NH2 is attached to benzene, the common name is aniline. So we are going to start numbering from this carbon atom. Therefore, chlorine gets 2, 3 and then 4. So 2 chlorine atoms are present at position number 2 and 4. And NH2 is going to get carbon number 1, but we are not going to indicate that number and it is written at the end. So the name of this compound is 2,4-dichloroaniline. Look at the next example. It is a toluene derivative. CH3 with benzene ring is called toluene. 3 substituents are present which are nitro, which are present at position 2, 4 and 6. But the position of this CH3 is not being mentioned. It is obviously carbon number 1. So the name is 2,4,6-trinitrotoluene, or it is also called as TNT. Another example is of a phenol derivative. OH with benzene is phenol. The 2 bromine atoms are at position number 2 and 6. So obviously this OH is getting carbon number 1. So the name is 2,6-dibromophenol. Students, another rule is if the substituents are all alike, their positions are indicated by numbering the substituents in a manner so as to give the lowest number to the substituents. Now look at the first example. We are having 3 bromine atoms. Now we are going to number it in such a way as to give lowest possible numbers. So we are going to start numbering from this carbon 1, 2, 3. That is why the name is 1, 2, 3 tribromobenzene instead of numbering from the other side. Similarly, here is another example. 1, 2, 3, 4 and 5. The methyl groups are at position 1, 2, 4 and 5. That is why its name is 1,2,4,5 tetramethyl benzene. Students, as I have mentioned earlier that in organic chemistry, common naming is very frequently used. Some polysubstituted benzene are still known by their common names. For example, this is mesitylene. This is having 3 methyl groups at position 1, 3 and 5. 1,3,5 trimethyl benzene is called mesitylene. Similarly, if we are having 4 methyl groups on benzene ring at position 1, 2, 4 and 5, it is called diurene. Similarly, meta-dihydroxy groups are present on benzene ring. This compound is called resorcinol, and these are the names that we frequently use for these compounds instead of IUPAC names. Students, the next topic that we have to study is the physical properties and structure of benzene. In the absence of polar substituents, arenes are typically hydrocarbons. We have studied all the physical properties of hydrocarbons. So in the absence of any polar substituent means that any heteroatom which is going to make a difference of electronegativity and create poles. For example, chlorine over here, due to the addition of chlorine on benzene ring, which is a typically hydrocarbon made up of carbon and hydrogens only. So addition of chlorine is going to induce polarity due to the difference in electronegativity of carbon and chlorine. Benzene, when it is not having a polar substituents, they are going to have low melting points and boiling points. They are having low solubility in polar solvents. All the 12 carbons in benzene, 12 atoms, that is 6 hydrogens and 6 carbons, they all lie in the same plane. Why? Because each of the carbon atom is going to be sp2 hybridized and making a triangular planar geometry. So benzene on the whole is also a planar structure. And you can see the presence of 3 double bonds which are alternating with the single bonds. Therefore, you can also observe the phenomena of conjugation. Students, now let us try to understand the structure of benzene on the basis of molecular orbital aspects. Now, when benzene was in the initial stage of being discovered and its properties were under investigation, scientists tried to write C6H6 in an open structure, but they were unable to adjust 6 carbon atoms and 6 hydrogen atoms in a open structure. So, a cyclic structure was suggested. If we try to draw benzene as alternating double bonds and single bonds, the two different Kekulé structures are obtained. And these two are equally valid resonance contributors. Now you can see these are the two Kekulé structures, a name based on the name of the scientist who suggested C6H6 in a cyclic way. Now you can see these are the two resonance contributors. Why? Because all the time these pi electrons are in conjugation. This double bond will shift over here, this double bond over here, and this double bond over here. And this conjugation and delocalization is always in continuation. That is why these are the two resonance contributors that could be written for the structure of benzene. Now students, you have to note down one thing, that all the carbon to carbon bond lengths in a benzene, whether it is between C double bond C or C single bond C, it is 1.4 angstrom. And this is a value which lies between a true C double bond C bond length, which is 1.33 angstrom, and a true C single bond C, which is 1.54. So the bond lengths of CC bond in benzene is between these two values, which is 1.4 angstroms. Now students, the two forms of the benzene that could be written, they can be combined in a resonance hybrid and conjugated system, which can be represented by a circle as in the Robinson structure. Why students? Because all these double bonds are continuously delocalized in the ring. And this Kekulé structure can be simplified and written as a Robinson structure, in which these pi electrons, which are continuously in resonance or in conjugation, they are delocalized within the ring. That is why it is represented by a circle, which is called Robinson's structure. Students, in benzene, all the carbon-carbon bonds are known to be of equal lengths. So there are no true double bond and single bonds. This is best represented by resonance hybrid, as we have discussed in the Robinson form. But since the key to organic chemistry is being able to understand the mechanisms, we always show the steps of a chemical reaction through a mechanism and drawing curved arrows to account for the positions of the electrons. So Kekulé structure gives a more precise description of the electron position that can avoid the confusion. Therefore, it is a good idea to use Kekulé representation when we are talking about mechanism of the chemical reactions, or we are trying to write any chemical equation. Students, although Kekulé gives best explanation of the structure of benzene, but it has some limitations that Kekulé structure failed to explain as to why. Benzene is less reactive. It shows dual character, that is, it shows addition reactions as well as substitution reactions. It has less heat of formation than expected, and it has equal carbon to carbon bonds. that we have already discussed about the bond lengths, that it is between the C double bond C bond and C single bond C bond. Now students, let us try to understand the structure of benzene on the basis of molecular orbital treatment. Spectroscopic studies have shown, and also X-ray analysis, that benzene is regular, flat, hexagonal, planar structure. All the 6 hydrogen atoms are coplanar with 6 carbon atoms. The bond angles between carbon-carbon and carbon is 120. Carbon, carbon and carbon. And also the bond angles between carbon-carbon and hydrogen, carbon, carbon and hydrogen is also 120 degrees. Thus each carbon atom is in a state of sp2 hybridization because each carbon atom is attached to 3 atoms. Carbon is attached to carbon on this side, carbon on the other side and one hydrogen atom, and all these 3 are sigma bonds. Combination of such 6 structures and overlap of 6 hydrogen atoms over here with one S1 produces the following sigma framework of the benzene. Students, each unhybridized p orbital of the 6 carbon atoms which are present perpendicular to the sigma framework. This is the sigma framework that we have already discussed. Now if we consider this plane as the sigma framework, all the p orbitals unhybridized of each carbon atom is perpendicular to the plane. Each p orbital is in a position to overlap parallel manner with the neighboring p orbitals to give a continuous sheet of negative charge, which is shown in this figure. Now students, this diagram is showing the sideways overlap. Now this p orbital being coplanar with the p orbitals of the neighbor, they can sideways overlap, making a continuous sheet of a negative charge above the plane and below the plane. Students, this structure, it results in extensive delocalized pi bonding which spreads all over the carbon nuclei of benzene. Delocalization of the p orbitals over the entire ring produce sandwich-like structure of benzene and decrease the energy of the molecule. Consequently, the molecule becomes more stable and less reactive. According to this molecular orbital picture, each carbon-carbon bond in benzene consists of one full sigma bond and a half pi bond. Because of this reason, the carbon-carbon bond length is equal and benzene shows substitution as well as addition reactions. Students, the conclusions can be drawn from molecular orbital treatment, and with the help of molecular orbital behavior, we conclude that benzene has a regular hexagonal structure with an inscribed circle, a hexagon with alternating double bond and single bond. So this is the modern representation of benzene, that either we are going to represent it in the Kekule structures or as Robinson structure. Now students, let us try to understand what is resonance. The possibility of different pairing schemes of valence electrons of atom is called resonance, and the different structures thus arranged are called resonance structures. Now let us look at the resonance structures of benzene. These are the 2 structures that were proposed by a scientist Kekule, and these are the 3 structures that were described by Dewar. The resonance is represented by a double-headed arrow. The following pairing scheme of the 4th valence or p electron of carbon atoms are possible in benzene. So students, these are the 5 contributing structure towards the true structure of benzene. The first 2 were given by Kekule, and the structure C, D and E was described by Dewar. Now students, the stability of the molecule increases with the increase in the number of resonance structures. Thus a molecule of benzene is chemically quite stable because it is going to have these 5 contributing structure. But the contribution of cacule structure in the true structure of benzene is a little greater as compared to Dewar structure because of this bond which is having a larger bond length, which is going to destabilize the benzene ring. Therefore, cacule structure is rather a stable structure that could be represented for benzene. But altogether these are called the resonance hybrid structures of benzene. Now students, let us try to find out the conclusions on the basis of the discussion. The molecule of benzene is quite stable due to the resonance structures. In fact, the benzene is a resonance hybrid of all the 5 structures A, B, C, D and E, in which cacule structure is A and B, which are the larger contributors as compared to Dewar structures. Therefore, benzene molecule can be represented either by the 2 cacule structures. The 3 alternating single and double bonds in the above structure are called conjugate bonds of resonating bonds. Since the structure of benzene is a resonance hybrid, therefore all the carbon-carbon bond lengths are equal but different from those of alkanes, alkenes and alkynes. It is an intermediate between the alkanes and alkenes.